September 4th, 1943, Room 283, Combined Operations Headquarters, Richmond Terrace, London. Brigadier Sir Bruce White, Royal Engineers, stared at blueprints that called for building 2 artificial harbours the size of Dover, transporting them across 50 miles of open water and assembling them on an exposed French coastline in 6 days. Every naval architect in Britain said it was impossible. In 9 months, they'd prove everyone wrong by landing 2.5 million men, 500,000 vehicles, and 4 million tons of supplies through harbours that shouldn't have existed. The combined chiefs of staff had just delivered their verdict. Each artificial harbour would need to handle 12,000 tons of supplies per day, in all weather conditions, without the protection of any natural coastline, without access to any port facilities. The requirement was staggering because the alternative was unthinkable. 2 months earlier, on August 19, 1942, the Allies had learned exactly what happened when you tried to capture a defended port. At Dieppe, 686 men had gone ashore. 3,693 became casualties in 9 hours. 907 Canadian soldiers died. 2,460 were wounded. 1,946 were taken prisoner, more prisoners than the Canadian Army would lose in 11 months of fighting across northwest Europe in 1944-1945. The Churchill tanks that were supposed to break through the German defences bogged down in the shingle before they reached the town. Of 30 Churchill tanks that landed, not one made it into Dieppe itself. The 42-ton Mark IV Churchills couldn't traverse the pebble beach. Their tracks spun uselessly on stones that shifted under their weight. Concrete barriers that intelligence hadn't detected blocked every exit from the beach. German machine gun positions on the cliffs above cut down wave after wave of Canadian infantry. The Royal Engineers assigned to breach the wire obstacles suffered 90% casualties, more than any other unit that morning. Major General John Hamilton Roberts had briefed his officers the night before. "Don't worry, men. It'll be a piece of cake." By noon, he was ordering a full retreat. The raid that was supposed to demonstrate Allied capability to capture a fortified port had instead demonstrated the opposite. Hitler's Atlantic Wall worked exactly as designed. The lesson was brutal and absolute. The Allies could not capture a fortified port. They would have to bring their own. But building a harbour wasn't the problem. Humanity had been building harbours for thousands of years. What the Allies needed was something that had never existed. A harbour that could be dismantled in Britain, transported across the English Channel, reassembled on an exposed French beach, made operational in days, not months, all while supporting the largest amphibious invasion in history, under fire. The Germans had spent 2 years fortifying every port from Scandinavia to Spain. 13 million cubic meters of concrete, 1.5 million tons of steel. Hitler's Atlantic Wall turned harbours into fortresses that would take months to capture and months more to repair after demolition. Rommel personally inspected the coastal defences. He ordered additional concrete bunkers built on cliffs overlooking every harbour, artillery positions with overlapping fields of fire, machine gun nests positioned to enfilade any beach approach, minefields extending inland from every potential landing site. Without a working port, any invasion force would run out of ammunition, fuel and food within days. A typical Allied serviceman required 6.5 pounds of supplies per day just to function. Food, water, medical supplies, ammunition. Multiply that by 150,000 men on D-Day alone. That's 975,000 pounds of supplies, 488 tons, every single day. And that didn't include fuel for vehicles, ammunition for sustained combat, or replacement equipment. Within a week, they'd need thousands of tons daily. Within a month, tens of thousands. Starvation would force them back into the sea. It would be Dunkirk in reverse. The greatest amphibious invasion in history would end in the greatest amphibious retreat. The physics alone seemed insurmountable. The English Channel wasn't a calm lake. It was 50 miles of unpredictable water that could generate 26-foot tides. The difference between high tide and low tide at Normandy was greater than a 3-story building. Any structure built at low tide would be underwater at high tide. Any structure built for high tide would be stranded on dry beach at low tide. The channel could generate waves that would destroy conventional harbour structures in hours. Storm systems rolled in from the Atlantic with minimal warning. Wind speeds could exceed 50 miles per hour. Wave heights could reach 15 feet in open water. Even larger waves could form when storms pushed water against the French coastline. The Normandy coast offered no natural protection, no bays, no inlets, no natural breakwaters. Just open beaches backed by cliffs and defended by the most sophisticated coastal defence network ever constructed. The harbours would need to create calm water where none existed, provide deep water anchorage for Liberty ships drawing 26 feet. Liberty ships carried the bulk of supplies from Britain. Each ship could carry 10,000 tons of cargo. But they needed deep water to operate. They couldn't come close to shore. Everything had to be offloaded to smaller craft or onto piers. The harbours would need floating piers that could rise and fall with the massive tides. Support roadways strong enough to carry 40-ton Sherman tanks. Connect to the shore with structures that wouldn't break in storms. Protect all of this with breakwaters that could withstand channel weather. Each harbour would need to be a mile long. Stand 30 feet above sea level at low tide. Include 6 miles of steel roadways floating on pontoons, all while withstanding storms that hit the channel without warning. And all of this would need to be operational within 2 weeks of D-Day. The conventional wisdom said it couldn't be done. Naval architects pointed out that no artificial structure had ever survived extended exposure to channel weather. The Royal Navy operated ships, not static structures. Ships could move with the waves, ride out storms, seek shelter. A harbour couldn't do any of those things. Military planners calculated that transporting the necessary materials would require resources that didn't exist. Britain was already stretched thin building ships, aircraft and weapons. Every ton of steel that went into an artificial harbour was a ton that didn't go into a battleship. Every cubic yard of concrete was concrete not used for airfield runways or coastal fortifications. Logistics officers argued that assembly under combat conditions was fantasy. The Normandy beaches would be under German artillery fire. Rommel had positioned artillery batteries on every high point overlooking potential landing sites. 80 Mimitor guns could reach far out to sea. Luftwaffe aircraft would bomb any large structure visible from the air. The Phoenixes would be impossible to camouflage. Concrete structures 200 feet long and 60 feet high would be visible for miles. Perfect targets for Stuka dive bombers. U-boats would torpedo anything being towed across the channel. Slow-moving tugs hauling massive concrete structures would be easy prey. German submarines patrolled the channel constantly. And even if everything arrived intact, who would assemble it? Combat engineers would be needed inland, supporting the advance. Infantry needed sappers to clear minefields and breach obstacles. The Navy would be busy with its own operations, protecting the invasion fleet, bombarding shore defences, evacuating wounded. The idea of civilian contractors working under fire was absurd. No construction company would send workers into a combat zone. No insurance would cover the liability. No union would allow it. The engineering challenges seemed designed to make success impossible. But Winston Churchill had been thinking about portable harbours since 1917. During World War I, as First Sea Lord, Churchill had proposed capturing small Dutch islands and using flat-bottomed barges mixed with manufactured caissons to form artificial harbours. The plan was abandoned when events moved too quickly, but the idea stayed with him. In May 1942, while Allied planners debated how to breach Hitler's fortress ports, Churchill issued a memo that read like science fiction. The memo, titled "Piers for Use on Beaches," was characteristically direct. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. That last line captured Churchill's approach perfectly. He didn't want to hear why it couldn't be done. He wanted to see how it would be done. The difficulties would become apparent during execution. Arguing about them beforehand was wasted time. By September 1943, those difficulties were arguing very loudly indeed. Bruce White and his Transportation 5 team at the War Office had been wrestling with Churchill's impossible demand for over a year. White was a World War I veteran, a former harbour builder. He understood the magnitude of the challenge. He also understood that failure wasn't an option. His team tested 3 completely different designs at a remote location in the Solway Firth, Scotland. The Solway Firth offered conditions remarkably similar to Normandy. 24-foot tides, exposed coastline, sandy beaches. The testing site at Garliston was evacuated of civilians and sealed behind military cordons. The entire area from Garliston through to the Isle of Withorn was declared off-limits. A military camp was constructed at Cairnhead to accommodate hundreds of engineers and support workers. Security was so tight that 15,000 workers would construct components in complete secrecy over the next year. Even the captains of the 60 obsolete ships, designated as block ships, thought they were heading to the Bay of Biscay right up until they were scuttled off Normandy. The Germans knew something was being planned. They didn't know what. The first design, called Swiss Roll, used large floating drums that could be towed to create an instant breakwater. The concept was simple: large hollow cylinders filled with air to make them float. Tow them to the invasion site. Anchor them in a line. They would create a barrier against waves. Tests at Garliston showed it worked. The drums created calmer water in their lee, but they had severe limitations. The roadways built on them couldn't support anything heavier than a lightly loaded small truck. A Sherman tank would go straight through the roadway into the water. The design was discounted from further development. The second design, called the Hughes Pier, was more ambitious. It employed concrete caissons, called hippos, that would sit on the seabed. Rigid steel roadways, called crocodiles, would connect the caissons. The concept seemed sound. Concrete caissons were proven technology. Steel roadways were straightforward engineering. But tests revealed fatal flaws. The caissons wouldn't form a sufficiently stable platform. The seabed at Normandy was mostly sand and gravel. Under the enormous weight of concrete caissons, the seabed would compress unevenly. Some caissons would settle more than others. The rigid steel roadways connecting them suffered severe bending and distortion as the caissons shifted. In some tests, the roadways snapped. The Hughes Pier was eventually discounted. The third design was the most complex. It combined elements that seemed impossible to reconcile. Concrete structures weighing thousands of tons that had to float. Steel roadways that had to flex with the waves without breaking. Pier heads that had to rise and fall 26 feet with the tide, while remaining stable enough to offload tanks. Breakwaters that could survive storms that generated 15-foot waves. This design worked. Barely. But it worked. What emerged from those tests at Garliston would require mobilizing British industry on a scale that rivaled weapons production. The artificial harbours, codenamed Mulberry A for the Americans and Mulberry B for the British and Canadians, would need 13 massive concrete caissons called phoenixes, 6 miles of floating steel roadways called whales, thousands of concrete and steel pontoons called beetles to support the roadways, 93 floating steel breakwaters called bombardons, 60 obsolete ships to be scuttled as an outer line of defence called gooseberries, pierheads called spuds that could handle the 26-foot tidal range. The code names were randomly assigned from a list. Mulberry meant nothing. Phoenix referred to the mythological bird rising from ashes. The caissons would be deliberately sunk to hide them from German reconnaissance, then resurrected when needed. Whale, beetle, spud, bombardon, all randomly selected. The randomness prevented German intelligence from deducing their purpose. The specifications for the Phoenix caissons alone staggered the imagination. There would be several sizes. The smallest, designated A1, weighed around 2,000 tons. The medium-sized B1 and B2 types weighed up to 4,500 tons. The largest, designated C1, weighed more than 6,000 tons. These were the ones that would form the main breakwater. A C1 Phoenix was 200 feet long, 60 feet high, wider than most buildings, taller than a 6-story apartment block, weighing more than a light cruiser, and they would be hollow. The Phoenixes had to be watertight enough to float when empty, strong enough to withstand waves and internal water pressure when partially flooded, heavy enough to stay in place when fully sunk, light enough to be towed 50 miles across open water. These requirements seemed contradictory. Building them would require 330,000 cubic yards of concrete, 31,000 tons of steel reinforcement, 1.5 million yards of steel shuttering, just for the concrete forms, and they would need 213 of them, in less than 9 months, while also building ships, aircraft, weapons, and ammunition. September 1943 through May 1944 became a race against physics and time. Construction sites opened along the Thames and Clyde rivers. At Stokes Bay in Gosport, 1,600 men worked day and night under extreme pressure to build 14 Phoenix caissons. Between November 1943 and April 1944, they constructed massive concrete structures in hastily built dry docks. The East India Dock in London had to be dammed across the entrance, de-watered, a bed of rubble laid down to support construction. 81,000 tons of rubble, specifically rubble from bomb-damaged buildings. The Blitz was building the foundation for Britain's revenge. The work was dangerous. Concrete pours had to be continuous to prevent weak joints. Workers operated in shifts around the clock, mixing concrete, laying steel reinforcement, vibrating the concrete to remove air pockets, all in open-air construction sites vulnerable to German bombing. At Stokes Bay, disaster struck during one launch. The caissons were too large to build in the water. They had to be built on shore and then launched sideways into the sea. A complicated system of winches and ball carriages moved each caisson to its launchway. On one launch, something went wrong. The caisson was moving toward the water on its launch rails. The winches were supposed to control the descent. Instead, the launch got out of control and collapsed the launchway. The massive concrete structure toppled. 3 men died instantly. 15 more were trapped beneath it. Rescue crews worked for hours to free them. Construction stopped for a month while the failed caisson was removed from the slipway. But the workers came back. They rebuilt the launchway. They continued construction because they understood what was at stake. The project required 200,000 workers across England and Wales, dozens of construction companies contributing specialised expertise. McAlpine, Costain, John Mowlem, Peter Lind, Wimpey, and dozens of smaller regional firms, each assigned specific components based on their capabilities and equipment. 200 tugboats to haul components across treacherous channel waters, ocean-going tugs capable of towing thousands of tons, 45,000 workers in direct employment on the project itself, another 155,000 in supporting industries producing steel reinforcement, concrete, specialized valves and equipment. Steel mills ran extra shifts producing reinforcement bars. Concrete plants operated around the clock mixing specialized marine-grade concrete. Valve manufacturers tooled up to produce thousands of flood control valves to exact specifications. The cost, £25 million, equivalent to building 50 destroyers, or 2,000 Spitfire fighters, or 50,000 military trucks, in 8 months. All conducted in complete secrecy. Workers were told nothing about the project's ultimate purpose. They built massive concrete structures without knowing they were building portable harbours. They welded steel roadways without understanding they would float on the English Channel. They fabricated pontoons without realising they would support 40-ton Sherman tanks. Security officers from MI5 watched constantly for loose talk in pubs and canteens. Workers who asked too many questions were quietly transferred to other projects. Letters home were censored for any mention of unusual construction activities. The entire project operated on a strict need-to-know basis. Foremen knew their section's specific requirements, and nothing more. Supervisors knew their facility's output targets, but not the destination. Engineers designed individual components without understanding how they integrated into the complete system. Only a handful of people, Churchill, White, McAlpine, and a few senior planners, understood the complete picture. This compartmentalization was essential, but created its own problems. Component manufacturers sometimes produced parts that didn't quite fit together. Assembly crews discovered mismatches only when trying to connect sections. Field modifications became routine. Engineers with cutting torches and welding equipment worked alongside assembly crews. Improvisation became as important as planning. Sir Malcolm McAlpine, chairman of the Contractors Committee, supervised the design and construction of the breakwaters. His company, Robert McAlpine Limited, built 10 of the 80 largest caissons. These weren't simple concrete boxes. Each phoenix was an engineering marvel. A phoenix was divided into 22 compartments separated by concrete walls. The compartments were arranged in 2 rows of 11. Dividing walls provided structural support and redundancy. If one compartment cracked and flooded, the others would keep the structure afloat during towing. Valves for controlled flooding were installed in each compartment. The valves were connected by shafts and couplings. The controls ran through an internal gangway that workers could access. To sink a phoenix, workers would open all the valves simultaneously. Water would flood the compartments in a controlled manner. The caisson would sink straight down rather than capsizing. Some phoenixes had sections at both ends roofed with concrete slabs. These sections provided crew quarters. Some phoenixes had anti-aircraft gun platforms built into the structure. Once sunk off Normandy, they would bristle with 40mm Bofors guns. Crews would live inside the caissons, manning the guns against Luftwaffe attacks. Each end of a phoenix was shaped into a swim end. The front and rear were streamlined to reduce water resistance during towing. Without swim ends, towing a 6,000-ton rectangular concrete box through 50 miles of open water would be nearly impossible. Even with swim ends, it required multiple ocean-going tugs and took over 24 hours. The Whale roadways presented their own nightmare. 16 kilometres of flexible steel bridges. Each section had to support 56 tons plus the 25-ton weight of a Sherman tank, 81 tons total, moving, in any weather. The roadways were made of steel spans mounted on pontoons. The spans were rigid. but the connections between spans had to flex. As waves passed underneath, different sections of roadway would be at different heights. If the connections were rigid, the stress would snap the roadway. If the connections were too flexible, the roadway would sag or wave. The solution was articulated joints. Each joint allowed a specific amount of movement: vertical movement to accommodate waves, lateral movement to prevent stress concentration. But not so much movement that vehicles couldn't cross. The beetles, the pontoons supporting the roadways, had their own specifications. Each beetle was made of concrete and steel. Each could support 56 tons plus 25 tons of vehicle weight. They had to maintain positive buoyancy under maximum load. They had to survive being constantly submerged and exposed as tides changed. They had to resist corrosion from salt water. They had to be quickly connectable to adjacent beetles. Lieutenant Alan Beckett of the Royal Engineers designed the whale floating roadways and the anchor systems. Beckett was brilliant, but difficult. He argued constantly with naval officers about design specifications. The Navy wanted conventional solutions. Beckett insisted on innovation. His design for the whale roadways was elegant in its simplicity: steel spans resting on floating pontoons. As the tide rose and fell, the roadways would flex at their joints, like a spine. The entire structure would undulate with the waves while remaining strong enough to support vehicles. The spuds, the pier heads, were Beckett's most elegant solution. Each spud consisted of a large pontoon platform. 4 massive steel legs extended down from the platform. The legs rested on the seabed. But they weren't fixed. The platform could slide up and down the legs. Hydraulic jacks maintained pressure to keep the platform stable. As the tide rose, the platform rose with it. As the tide fell, the platform descended. Ships could moor alongside at any tide level. The whale roadway connections had enough flex to accommodate 26 feet of vertical movement. But Beckett's anchor design caused problems. He'd developed specialized anchors called kite anchors. His tests showed they had extraordinary holding power. A kite anchor could hold against forces that would rip conventional anchors from the seabed. The design used multiple flukes that dug deeper under load. The more tension applied, the deeper they gripped. Beckett wanted kite anchors used for everything, especially for the bombardons. The Navy dismissed his claims. They'd used conventional anchors for centuries. They saw no reason to change. This decision would prove catastrophic. The bombardons, the floating outer breakwaters, were engineering marvels in their own right. 93 massive steel structures, cruciform in cross-section. Each arm of the cross was hollow. The structures could be ballasted with water to adjust their floating depth. They weighed thousands of tons each. The genius of the bombardon design was in how it handled waves. It didn't resist waves. It absorbed them. The cruciform shape allowed the structure to oscillate with wave motion. As a wave approached, the bombardon would rise. As the wave passed, the bombardon would fall. The oscillation absorbed wave energy without creating dangerous stress concentrations. They would be anchored at the outer reaches of the harbour, the first line of defence against channel storms, but only if the anchors held. By May 1944, components were complete and moving to assembly points along the south coast. The scale of the logistics operation defied comprehension. Phoenixes that weighed up to 6,000 tons had to be towed from construction sites to staging areas. Many had been deliberately sunk to hide them from German reconnaissance aircraft. Luftwaffe reconnaissance flights photographed the south coast of England constantly. Intelligence officers studied every photograph for evidence of invasion preparations. They saw the Phoenixes. They just didn't understand what they were looking at. The phoenixes appeared as large concrete structures in harbours. German intelligence analysts assumed they were air raid shelters, or coastal defence structures, or dock facilities. The idea that they were components of artificial harbours never occurred to them. But, to make the deception work, the phoenixes had to disappear. They were deliberately sunk in harbours along the south coast. Valves were opened, the compartments flooded, the massive structures settled to the bottom. Only their tops remained visible, looking like half-submerged wrecks. Now they would need to be refloated, resurrected. This is where the operation nearly failed before it began. The Royal Engineers had drawn up plans to refloat the sunken caissons. The plan involved pumping water out of the compartments. As the compartments emptied, the phoenixes would rise. Simple in theory. But the pumps mattered. American salvage expert Captain Edward Ellsberg reviewed the Royal Engineers' plans. Ellsberg was a legend in salvage operations. He'd raised sunken ships all over the world. He knew what would work and what wouldn't. His assessment of the Royal Engineers' plan was damning. The pumps they planned to use were designed for moving sewage horizontally. They were centrifugal pumps optimized for high volume, low pressure. They couldn't provide the lift needed to pump water up and out of 60-foot-tall structures. The pumps would run continuously. Water would circulate inside the caissons. But the water level would never drop enough for the phoenixes to rise. Ellsberg's report reached Churchill. Churchill intervened personally. He took the refloating operation away from the Royal Engineers. He gave it to the Royal Navy. Commodore Sinclair Mackenzie was put in charge. Mackenzie moved fast. He assembled every salvage barge in the British Isles. Every high-capacity pump was requisitioned. New pumps were sourced from anywhere they could be found. The phoenixes were refloated one by one. It was a delicate operation. Pump too fast, and the caisson might rise unevenly, capsizing. Pump too slowly, and you'd miss the tide window needed for towing. Each phoenix took hours to refloat, but they all came up. By early June 1944, over 400 components weighing approximately 1.5 million tons were assembled and waiting. 146 Phoenix caissons at Dungeness and Selsey, 93 bombardons at assembly points along the south coast, 60 block ships at Scottish ports and Poole Harbour, thousands of beetle pontoons, miles of whale roadway sections, 132 tugs standing by, crews briefed, routes planned. The largest maritime construction project in history was ready to cross the Channel. June 6, 1944, D-Day, 0300 hours. While 156,000 Allied soldiers stormed the beaches of Normandy, the first elements of the Mulberry harbours were already moving across the Channel. The timing had to be precise. The components couldn't arrive before the beaches were secured, but they had to arrive as soon as possible afterward. Every hour of delay meant supplies weren't getting ashore. The bombardons went first. These massive floating breakwaters had to be positioned before anything else. They were the outer wall. Without them, everything else would be exposed to wave action. Following them came the block ships, 60 obsolete merchant vessels and warships sailing on their final voyage. They had departed from Poole Harbour and Scottish ports days earlier, loaded with explosive scuttling charges. Crews who'd nursed these ancient ships across the Channel knew they were going to sink them. Many of the ships were so old, their crews wondered if they'd make it. Among them was the French battleship Courbet, launched in 1911, veteran of World War I. She'd escaped from France when it fell in 1940, served with the Free French forces. Now she would become a breakwater, a Dutch cruiser, British destroyers, merchant ships from half a dozen nations. Ships that had fought in 3 wars were about to become walls. Behind the block ships came the phoenixes. 132 tugs strained against their tow cables. Each Phoenix weighed thousands of tons. Some were being towed in pairs, some individually. The crossing took 18 to 36 hours depending on weather and towing speed. But all were converging on two locations: Mulberry A off Omaha Beach at Saint-Laurent-sur-Mer for the Americans, Mulberry B off Arromanches at Gold Beach for the British and Canadians. The first Phoenix reached its designated position at dawn on June 8, 1944, D-Day +2. Royal Engineers from 20 Port Group and US Navy Seabees began the assembly process. They had rehearsed this at Garliston, but rehearsals had been conducted in calm Scottish waters with no one shooting at them. This was the English Channel, under fire, with German artillery positions on the heights inland still operational. The assembly sequence was precise and unforgiving. First, the block ships were scuttled in pre-arranged positions. Operation Corncob was the code name for scuttling the block ships. Survey teams had marked exact positions with buoys. Each block ship had to sink in the right location to create a continuous line. Too far apart and gaps would let waves through. Too close and they'd damage each other during scuttling. The ship's captains opened seacocks. Explosive charges detonated. Within minutes, the vessels settled onto the bottom. Their superstructures remained above water, creating the outer line of defence called gooseberries. By June 11th, the gooseberries were complete at both Mulberry sites. The block ships created immediate calm water. Even before the Phoenixes were in place, the gooseberries were saving lives. Landing craft could shelter in their lee. Ships could anchor in calmer water. Casualties from capsized boats dropped immediately. Next came the Phoenixes. Each caisson was manoeuvred into position by tugs. Survey teams guided them to exact GPS coordinates. But GPS didn't exist in 1944. They used sextants and trigonometry, shore markers, constant communication between tugs. When aligned correctly, valves were opened. Water flooded the internal chambers. The massive concrete structures sank in controlled descents. Air trapped in the compartments escaped through vents. Water filled the void. Positioning had to be exact. If a Phoenix was even slightly off target, it couldn't be moved once sunk. A 6,000-ton concrete block on the seabed wasn't going anywhere. If it was misaligned, they'd have to work around it or abandon that section of harbour. The first Phoenix sank at Arromanches at dawn on June 8th. By June 9th, multiple Phoenixes were being positioned simultaneously at both sites. By June 14th, half of the 146 Phoenixes were in place. By June 15th, a continuous arc of caissons stretched for 5 miles at Arromanches, from Tracy-sur-Mer in the west to Asnelles in the east. At Omaha Beach, the American Mulberry was 3 days behind schedule but progressing. The Americans had been less careful about exact positioning. Speed was more important than perfection. This would prove to be a mistake. By June 18th, both harbours had 2 operational piers and 4 pier heads. The whales, the floating roadways, were in place, connected to the spuds. Ships were already mooring alongside. Supplies were flowing ashore. In 6 days, working under fire, the Allies had constructed 2 artificial harbours, each a mile long, capable of handling 7,000 tons of supplies per day, more than enough to sustain the invasion. The engineers and construction crews were exhausted, but they'd done it. The impossible had been accomplished. Then, on the night of June 18th, everything changed. June 19th, 1944. 0200 hours. Meteorologists watching weather patterns over the Atlantic saw a storm system forming. This was unusual for June. The English Channel typically saw its worst storms in winter. Summer storms were supposed to be mild, but the barometric pressure was dropping. Wind speeds were increasing. By dawn, Waves in the channel were building. By mid-morning, the storm was hitting full force, a nor'easter, force 6 to 8 winds. Sustained winds of 35 to 45 miles per hour, gusts exceeding 50 miles per hour, waves 12 to 15 feet high in open water, higher near the coast where the storm surge pushed water against the shore. Meteorological records would later show this was the worst storm to hit the Normandy coast in 40 years. The Mulberry harbours had been designed for summer weather. The engineers had calculated wave heights, wind loading, and structural stresses based on typical June conditions. This was not typical. At Mulberry A off Omaha Beach, disaster struck within hours. The bombardons, the floating outer breakwaters, broke free from their moorings. The conventional anchors the Navy had insisted on using couldn't hold against the storm's force. One by one, the anchors ripped free from the seabed. Free-floating bombardons weighing thousands of tons became battering rams. The storm drove them toward the inner harbour, toward the Phoenixes, toward the whales, toward everything the engineers had spent 6 months building and 6 days assembling. The first bombardon struck a Phoenix caisson with devastating force. The impact cracked the concrete. The caisson's structural integrity was compromised. Seawater began seeping through stress fractures. More bombardons broke free. They smashed into other Phoenixes, into the whale roadways, into each other. The Phoenixes had been designed to withstand wave action. Waves pushed against them gradually. The concrete could absorb that stress, but they hadn't been designed to be struck by free-floating steel structures travelling at several knots. That was impact loading, a completely different kind of stress. 21 of the 30 Phoenix caissons at Mulberry A were destroyed. Some cracked vertically, their walls splitting. Some broke apart, sections collapsing. Some filled with water from internal stress that burst compartment walls. The whale roadways fared even worse. Sections broke apart at their articulated joints. The joints were designed to flex, not to survive being struck by massive steel objects. Pier heads were smashed. The carefully balanced spuds toppled. Their legs bent under impacts they were never designed to withstand. Landing craft that had sought shelter inside the harbour became missiles. The storm drove them against the structures. British LCTs, landing craft tank, were particularly problematic. 5 British LCTs broke free and were driven into the American harbour. They smashed into Phoenixes and whales, adding to the destruction. 650 LCTs had been in the area around both Mulberry harbours. Only 330 survived the storm. The Americans watched helplessly as 3 months of work and tens of thousands of man-hours disintegrated before their eyes. There was nothing they could do. Navy crews tried to secure some of the drifting craft. Some tugs attempted to tow bombardons away from the inner harbour. But the storm was too powerful, the wind too strong, the waves too high. By June 22nd, the assessment was complete. Mulberry A was irreparable. The harbour was dead. At Mulberry B off Arromanches, British engineers fought to save their harbour. They'd been more careful with the mooring procedures. Lieutenant Beckett had insisted on double anchoring. His concerns about anchor strength had led to additional precautions. Some Phoenixes were secured with multiple conventional anchors. Others were anchored and additionally stabilized with ballast. But the storm still inflicted terrible damage. Several bombardons broke free. They had to be cut loose immediately. If they reached the inner harbour, they'd destroy everything. British Navy crews worked in 15-foot waves to cut the anchoring cables, deliberately sacrificing the bombardons to save the Phoenixes. Sections of whale roadway broke loose. Several Phoenixes suffered stress fractures, not as catastrophic as at Omaha. but serious enough to threaten the harbour's operation. For 3 days the storm raged. June 19th, 2021. 3 days of winds, waves and destruction. When it finally broke on June 22nd, the assessment began. Mulberry A was gone, beyond repair, beyond salvage, a total loss. Mulberry B had survived, barely, badly damaged, but operational. The loss of Mulberry A forced immediate changes to Allied logistics planning. Major General John Hamilton Roberts, who commanded the 2nd Canadian Infantry Division, was put in charge of salvage operations. He'd seen enough disasters at Dieppe. He wasn't going to preside over another one. Anything salvageable from Mulberry A would be transported to Mulberry B. Salvage crews worked around the clock in the wreckage. Diving teams assessed Phoenix sections underwater. Those with repairable cracks were patched and refloated. Those damaged beyond repair were abandoned. Usable Phoenix sections were towed 20 miles east to Arromanches. The towing operations took days. Each caisson required multiple tugs and careful navigation. Whale roadway sections were recovered from the beaches and shallows. Some were bent but repairable. Others had snapped and were written off. Beetles that hadn't been destroyed were collected and inventoried. The ones with intact pontoons were towed to Mulberry B. The damaged ones were stripped for parts. Nothing was wasted. Every piece of steel, every section of roadway, every functional valve was salvaged and reused. The Phoenixes at Mulberry B were doubled up for additional protection. 2 rows of caissons instead of 1. The outer row would take the brunt of future storms. The inner row provided backup if the outer row failed. The double row also created additional wave suppression. Waves that passed the outer row would hit the inner row already diminished in energy. This redundancy made the harbour significantly more resilient. The caissons were filled with dredged sand for additional stability. This was a massive undertaking. Dredging equipment was brought across from England. Pumps removed seawater from the Phoenix compartments. Then sand slurry was pumped in to replace it. Each Phoenix could hold hundreds of tons of sand. Filling them took days per caisson, but once filled, they became immovable. No storm could shift a 6,000-ton concrete structure filled with sand. Engineers also implemented lessons from the storm. Additional mooring points were installed. Redundant anchoring systems were added to critical structures. Weather monitoring was intensified. Meteorologists tracked every low-pressure system forming over the Atlantic. When storms approached, crews secured everything that could move. Landing craft were moved to maximum safe distance. Loose equipment was stowed. Personnel were reduced to essential crew only. The engineers were determined that another June 19th would never happen again. This turned the hollow concrete boxes into solid structures that couldn't be moved by storms. Gaps between Phoenixes were plugged with rock-filled steel mesh gabions. Every weak point was reinforced. The British were determined that Mulberry B would survive. The Americans at Omaha fell back on improvised methods. LSTs, landing ship tanks, were beached at high tide. The bow doors opened. Vehicles drove directly onto the beach. Supplies were offloaded. When the tide came back in, the LSTs refloated and returned to England for more cargo. The favourable geology of Omaha Beach made this possible. The beach slope was gradual enough that LSTs could beach without damage. The sand was firm enough to support vehicles. Rhino ferries, power-driven pontoons, carried cargo from ships anchored offshore to the beach. DUKWs, amphibious trucks called ducks, shuttled back and forth constantly. Ship to shore to ship, moving supplies around the clock. American ingenuity and determination compensated for the loss of Mulberry A. By D-Day +30, Omaha Beach was exceeding the intended offload rate. 9,000 tons per day, without a functioning Mulberry harbour, the Americans had proven that over-the-beach logistics could work, with enough improvisation, enough vehicles, enough determination. And favourable beach conditions. But Mulberry Bee at Arromanches was the real story. The harbour that Churchill had insisted must be built. The harbour that naval architects said couldn't survive Channel weather. The harbour that was supposed to last 90 days. It operated for 10 months. 10 months of continuous operations in one of the most challenging maritime environments on Earth, through the entire winter of 1944 to 1945. Winter in the English Channel means storms that make June's nor'easter look mild. Gale-force winds became routine. Wave heights exceeded 20 feet during major winter storms. Temperatures dropped below freezing. Ice formed on metal surfaces. Crews working on the Spuds and Phoenixes faced brutal conditions, through storms worse than the one in June. Several times, meteorologists predicted weather that would destroy the harbour. Each time, the reinforced structures held. The double row of Phoenixes worked exactly as designed. The outer row absorbed the worst impacts. The inner row provided backup protection. Waves that reached the pier heads were already diminished, through German attempts to destroy it with mines, sabotage, and air attacks. The Luftwaffe bombed Mulberry Bee repeatedly during autumn 1944. Anti-aircraft crews manning guns on the Phoenix caissons fought off attacks. Barrage balloons surrounded the harbour. Their steel cables posed lethal hazards to low-flying aircraft. Several German bombers were destroyed when they flew into the cables. German E-boats, fast attack craft, attempted to infiltrate the harbour at night. Royal Navy patrol boats intercepted most of them. Some got through and laid mines. Minesweepers worked constantly to keep the approaches clear. German fragmen, combat swimmers, were captured attempting to attach limpet mines to Phoenix caissons. But the harbour kept operating. Nothing the Germans tried could shut it down. The Phoenixes stood firm through it all, reinforced with sand, doubled up for protection. They created calm water in the most exposed section of the Normandy coast. The whales flexed with the waves as designed, even in winter storms. The articulated joints absorbed stress. The beetles maintained buoyancy. The Spuds rose and fell with the tides. 26 feet, twice a day, every day, for 10 months. The statistics tell the story better than words ever could. Through Mulberry Bee at Arromanches, 2.5 million men came ashore, 500,000 vehicles, 4 million tons of supplies. Every Sherman tank that fought in France came through Mulberry Bee, every jeep, every truck, every artillery piece, every round of ammunition, every gallon of fuel, every ration. Without Mulberry Bee, the Normandy invasion would have stalled. Cherbourg wasn't captured until June 26th, but the port was so thoroughly demolished by the Germans that it took until September to clear it, 3 months to make it operational. By that time, Mulberry Bee had already landed armies. Antwerp, the greatest port in Europe, wasn't captured until September 4th, and it took another month to clear the Scheldt estuary of German forces. The port didn't become operational until November. By that time the war was nearly over. Mulberry Bee sustained the invasion, made the breakout from Normandy possible, kept supplies flowing when there were no other options. The Mulberry harbours revealed fundamental truths about modern warfare. Industrial capacity determines strategic options. Engineering innovation can neutralize conventional defences. The impossible becomes possible when the alternative is unacceptable. After the war, Albert Speer sat in the dock at Nuremberg. He was asked about German defensive preparations, about the Atlantic Wall, about the fortifications that Hitler believed would make invasion impossible. His statement captured the German perspective perfectly. To construct our defences we had in 2 years, used some 13 million cubic meters of concrete and 1.5 million tons of steel. A fortnight after the Normandy landings, this costly effort was brought to nothing because of an idea of simple genius. As we now know, the invasion force brought their own harbours and built, at Arromanches and Omaha, on unprotected coast, the necessary landing ramps. 2 years of German fortification, 13 million cubic meters of concrete, 1.5 million tons of steel, rendered irrelevant by 9 months of British engineering. General Dwight D. Eisenhower declared, "Mulberry exceeded our best hopes." General Omar Bradley called it one of the most inventive logistical undertakings of the war. Air Chief Marshal Sir Arthur Tedder concluded, "The whole question of the invasion of Europe might well have turned on the practicability of these artificial harbours." President Roosevelt told Labour Secretary Francis Perkins, "You know, that was Churchill's idea. Just one of those brilliant ideas that he has." The technology developed for Mulberry had lasting impact beyond the war. 4 surplus Phoenix caissons were used to plug gaps in Dutch dikes after the catastrophic North Sea flood of February 1, 1953. Water had breached the dikes. Thousands of people were at risk. The Dutch government needed to seal the gaps immediately. They remembered the Phoenixes. 4 caissons were towed from Britain to the Netherlands, positioned in the breaches, sunk, the gaps sealed, thousands of lives saved. Those 4 Phoenixes now house the Watersnood Museum, the Flood Museum, at Overkerk. Visitors can walk through the same concrete chambers that once formed a harbour off Normandy, touch the walls that withstood Channel storms, see the compartments that flooded to sink them into position. Several Whale roadway sections were reused as bridges in northern France. The floating roadways that carried Sherman tanks became permanent bridges over rivers. Some are still in use today, 80 years later. In the 1960s, 3 Whale spans from Arromanches were installed at Fort Dagenham. Cars could drive directly from the assembly line onto ships. The same roadways that had carried tanks in 1944 now carried automobiles. 2 Phoenix caissons from Mulberry B were moved to Portland Harbour in 1962. 8,000 tons of water had to be pumped out to move them. They now serve as windbreaks for ships berthed at Queen's Pier. In 2017, 6 sculptures were erected on top of them. 2 British sailors, 2 dockyard workers, 2 American GIs, a permanent memorial to the men who built and operated the Mulberry harbours. At Arromanches, the remains of Phoenix caissons still sit offshore. They've been eroding for 80 years, but they're still there, still visible from the beach. Concrete testimony to what British engineering accomplished in 9 impossible months. Winston Churchill's impossible demand, piers for use on beaches, had been met. The engineers who said it couldn't be done had been proven wrong. The naval architects who predicted failure had watched the harbours survive storms that should have destroyed them. The Germans who spent 2 years building the Atlantic Wall discovered that fortification could be bypassed by innovation. The Mulberry harbours weren't just a triumph of engineering. They were proof that industrial democracy could outthink and outbuild totalitarian efficiency, that systematic innovation could defeat brute force fortification, that the impossible becomes possible when failure means defeat. Bruce White's team had been given requirements that seemed designed to fail. Build harbours that can be dismantled, transported and reassembled in days. Make them survive Channel weather, support the largest amphibious invasion in history. Do it in 9 months, while fighting a war. They succeeded. 213 Phoenix caissons, 16 kilometres of floating roadways, 132 tugs, 200,000 workers, 1.5 million tons of material, 2 harbours the size of Dover, assembled in 6 days, operational for 10 months, 2.5 million men, 500,000 vehicles, 4 million tons of supplies. The numbers are staggering, but they tell only part of the story. The real story is about workers at Stokes Bay who came back after 3 of their colleagues died, about engineers who designed structures that had never existed before, about tugboat crews who towed 6,000-ton concrete blocks across 50 miles of open water, about salvage experts who refloated caissons the Royal Engineers said couldn't be raised, about British and American forces working together to build something impossible. The assembly lines didn't win the war. The factories didn't win the war. The phoenixes didn't win the war. But they made victory possible. They created the logistics infrastructure that turned strategic vision into tactical reality. They proved that engineering could solve problems that seemed to have no solution. And in the end, that's what Mulberry was always about. Not just building harbours, building the future, 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 building the future.